Thank you for giving me the opportunity, John and Joel, to share some thoughts with you today. I'm a chemist, I'm a material scientist, and I look at the circular economy and our issue from the perspective of the materials that we use, that we design our products, and look at the system. At this moment in time, we want to do the right thing. And when we want to do the right thing, we're trying to figure out what's the approach. You know, there's cradle to cradle, there's resilience, there's natural capitalism, the circular economy, there's responsible care, there's limits to growth. There's so many wonderful approaches out there for us to pick from. It's sometimes confusing that there are so many. And what I'm really concerned about is in our polarized society, instead of looking at all these wonderful ways of approaching things, there almost has to be some contention. Well, this is the right way and this is the wrong way. And man, we're facing so many problems. If someone wakes up in the morning and one of these approaches speaks to their heart, we need them to be embracing that and doing that. And who among us is so presumptuous to pick and choose which one is the best one? There are so many problems that we've really got to look at the big picture and see that everything here has merits and things that aren't listed on here. Because the problems are diverse and we need diversity of eyes and ideas to solve these problems. So I'm going to share with you how I look at the materials economy. Now, I want to give a disclaimer. I do not claim any gifted insight. I don't claim to have the answers to the world's problems. I've lived my life, I've come to see the world in a certain way, and I'm going to, with given amount of vulnerability, share that with you, but I don't have the presumption to say this is the right way. It's the way that works for me, and so I want to share it with you. We want our products to be in the state of use and reuse. That is the highest form of sustainability that we want to achieve. Sometimes we think about humans in the natural world and we try to pull ourselves out of it. We humans are part of the natural world. Use and reuse is abundant in nature. One example, the hermit crab. When a hermit crab finds a shell, lives in that shell, when it gets too big, it vacates that shell and finds another shell. This kind of durable goods is abundant in nature. We humans in the human-built world have plenty of products that we want to either be durable or reusable. When we do this system of use and reuse, it's important to realize what we're asking is that the materials conserve their composition, their chemistry, and they conserve their form. So in a use and reuse cycle, we want to maintain both the molecularity and the structure. But then there's this thing called entropy. And entropy comes, and inevitably, stuff happens. At that point, we're out of our use and reuse cycle, so we have to go to the next cycle, what I call the manufacturing and mechanical recycling system, where we take our products and cycle them through materials and components. In the natural world, a bird will find a twig and pick it up and build a nest. A beaver will find like a tree and make a dam. We in the human-built world, we take waste plastics, we sort them, we granulate them, we remake them. And the idea is that we recycle this plastic through mechanical recycling. The difference in this system is now what we're doing is we are allowing the shape, the form to change, but we're hoping to maintain the chemical composition. That's the distinction between use and recycle, is we are changing the mechanical structure of the material, but we're hoping to maintain the chemical structure. But again, entropy rears its beautiful head, and what happens is the polymer chains and the fibers start to break down, and we can't maintain that mechanical properties, and thus we have to go counterclockwise in the system to what I find the most beautiful opportunity for us, what I call the materials metabolism, where we take materials and components and go to molecules and ingredients and back and forth, not through chemical recycling, but through molecular reprocessing and synthesis. And this is where nature has got such an opportunity to teach us. 3.8 billion years of evolution. Here is a very old picture of my daughter, who is now 10 years old, and my wife, and they're eating food. What happens in biology when we eat a material? Okay, we take large molecules, and through the process of catabolism, we make small molecules. But that's not it. What else happens as we're eating our food? At exactly the same time, we grow hair, we grow fingernails, we grow blood cells. In nature, the deconstruction and the construction, where we through anabolism take small molecules and make large molecules, happens at the same time. We in human-built world does not have this corollary. Think about it. If we humans designed biology, we would say, oh, only have lipids for breakfast, only have carbohydrates for lunch, only have protein for dinner, because heaven forbid we can't mix them up. Nature doesn't care about mixtures. And as long as we hold ourselves to the reality that we must have separate mixtures, you know what? We'll always have to have separate mixtures. Biology doesn't. And the reason is because in this case here, we have all the degrees of freedom. We change not only the chemistry, but we also change the form at the same time. And we couple the energetics. All right? While we're breaking and making molecules, we're creating and releasing energy through this magical molecule ATP and these beautiful phosphate groups that create a molecular battery. Now at this apex of the pendulum, we can come back down, and through regeneration, we're interacting now with the natural world and natural resources. And of course, there's all kinds of abundant examples: termites and termite mounds, dung beetles, bees pollinating, lions eating prey. We're scratching at the surface of some regenerative products, some packaging, some food, some, textiles and products, but we get so much further to go. All right? And so what we need to do, then in the final stage of this thing, we have the natural resources, and this is our happy place where we imagine all these pristine ecosystems. Now here's the thing. The way I look at this is a pendulum in which we have the human-built world going on the clockwise direction, the natural world going in the counterclockwise direction, and the intersection at the bottom is our measure of sustainability. And that what happens is it'd be foolhardy to believe that there's no intersection, but we want to minimize that intersection and make that intersection as and here is where the problem is. I'm a member of the Club of Rome. We think of systems all the time. And one of the things we got to realize is we got to have humility when we look at systems, because it's not the things we put on the map that's going to mess us up. It's the things we leave out. During recycling, there's leakage, and what happens is that leakage creates porosity at that intersection, and we lose a little sustainability. When we do the materials metabolism, there's leakage. We get more porosity, and we lose a little more sustainability. When we do regeneration, there's more leakage. We lose a little more sustainability. No one in their maps usually puts these things. All right? Nope. And what do we do with leakage? That's an equal issue, or perhaps even a more important issue. So we have human behavior where we have to design our products to facilitate the adoption of behavioral changes. But we also have to have technology that creates materials and products that are actually in harmony and compatible with nature. It's not one or the other, it's actually both. And we need to learn to work, not only the commercial people, not only the development people, not only the manufacturing people, not only the researching people, not only the recycling people, but as a community, we have to look at all of these approaches and start talking to each other more often, okay? And what I love about the apex of this, I am a chemist, I'm a material scientist, I feel the opportunity for all of us is to look at how we can invent these materials to support an ecosystem where humanity adopts these behavioral changes, but does it in partnership not only with nature, but with technology. And so as John mentioned, the field of green chemistry is near and dear to my heart as how does the scientist, the day they stop beginning to invent something, anticipate these realities. And here's my last thought I want to leave you with. If you Google every chemistry program on the planet, every material science program on the planet, you will find not one university requires a chemist or a material scientist to learn anything about what we're talking about today. So we're asking to invent solutions to people who are not provided the skills. So let's get on with it. Let's collaborate not only with industry and other things, but let's go to the universities and suggest maybe you might want to change your curriculum. And that's what green chemistry is all about. Thank you.